and we come up with these vectors added together give us this large vector here. The large vector here is the displacement vector and 18.8 miles at 320 degrees. Okay. Now, the next part says find the x and y components. Who knows what an x component is? Marissa. Okay, good. So it's the value of the vector in the x direction. So, oops. That would be the vector in the x direction. So that would be its x component. This would be its y component, because that's in the y direction. Okay? Running along the x-axis, running along the y. You can check yourself with sort of like, is there positive or negative? Because you can see like this is in the positive direction in the x, and it's going down, so it's in the negative direction in the y. How would I find out what this value is? We'll measure it with our ruler. What am I going to do later? I'm going to mathematically calculate it. So the x1, you can do it with yours too, comes out to be, okay, 7.3 centimeters. Now we need to change that to miles, right? And remember, for this, 1 centimeter equals 2 miles. So 1 centimeter is 2 miles. So that gives us 2 times 7.3, or 14.6 miles. Let's do the y. Six centimeters. $12 miles, right? Okay? So that's x and y components. Yes. Oh, good point. Yeah, that would be negative 12 miles. Or 12 miles. Negative 12 is fine. Yes. Thank you. Well, yeah, I mean, it's just, remember you could put negative 6 here. That's fine. It's just realizing that it's in the negative direction is the key. Okay, so it does we should have the negative 12. If you want negative 6, you could. It seems a little weird to me to write negative 6 centimeters, just because of the measurement. But the reason for that is because the scale is centimeters to miles, and the negative just tells us what direction that's going in, right? It's negative on the axis, so it would be okay to do that. Okay, good. Yeah, it's the green one over there. Moving on to another one. Oh, so we've been adding these vector components, right? I mean, we've been adding vectors and putting them together and summing them up. So if we have, when we add vectors, how do we arrange them to add them? Head to tail, right? Now we've added 2 vectors, but we could add 5 or 6. Doesn't really matter. We could add as many as we want. So let's make some vectors here. We'll have a vector A. We'll have a vector B. Whoops. Sorry. We'll have a vector C. A vector D. And a vector E. Like that. Okay. Now let's find A, let's find R, the resultant, which would be A plus B plus C plus D plus E. Okay? Exactly. So, Kendra, start with A. Put it somewhere. Go grab it and put it somewhere on the board. Don't put it on the wall. Although I did ask when they built this new building that I wanted a smart wall, not just a smart board, but they did not. And they actually, now I have an old smart board in comparison. Yeah, just put it down in the white space. It's on infinite cloner, so just grab it. No, you don't need 8 of them, just 1. That'll work. Now, Michael B, and then just keep going in line. We're going to add these all up, so Leanne would be after Michael, so keep filter it up there. Leanne. So there's B. And now Leanne's going to get C. Press it. Don't be afraid to press. There you go. Click off of it. Now grab it. Good. And D. And E. Now Emma, go up there and put R on. It's set for you. Just press where you think it begins to put where it ends. Good. There's our R, right? That's nice, right? What if we did this? What if we did E plus D plus C plus B plus A? Does that equal R? Let's see. Start us off. Let's see. Put E. Start off with E. And then Carolyn, you'll go after Vera. E is placed. Now she's going to do D. Hold on a second. It's all right. Now come fix it. Carolyn, how's it got to be? Nope, it got to be, see, here's the head of that one. There you go. Good. And now you do C, Mary. Okay, and then Maya, she's going to do B. Good. And then Julia is going to be B-A, I mean. Sorry. And now I'm going to select it all and move it over so it's all on there. And then let's see, Tyler, see if R, it's the same R. So we started at the yellow E and ended at the black A. Oh, wait, no, move it. We started here, I'm sorry. I infinite cloned it, but I could do it that what you were doing. Now it's good. Let's see if they, that's all right. Does it match up? Whoops. Pretty close, right? Same thing. So, good. Okay, good. Yes. So it doesn't matter what order we add them in. They'll still sum up to be the same. But it's not one plus the other. It's not a simple addition. It's vector addition, right? So the direction matters. Now there's this concept that's sometimes useful that's called the equilibrium of the vector of a vector, which is the vector in the opposite direction, or minus 180 degrees. So instead of pointing like this, our equilibrium is the same magnitude, but it points like that. Whoops. So I'll flip this left, right, and then I'll flip it up, down. I'm going to change its color, move that over. What? There's what's called our equilibrium, E. What's the sum of R plus E? Right. R plus E equals 0. See if I overlap these on there, we get 0. So if R is at (9 degrees). Oh, I'm sorry, not 9 degrees. But if I do the, let's have a reminder here of our this here was 0 degrees, right? Up here was 90 degrees. That would be 180, and that would be 270. Okay? And in the middle, you'd have 45 degrees, 135 degrees, 215 degrees, 300, oh wait, no, 225, yes, thank you. 315 degrees, 30, 40, yeah. Okay, just as a reminder. So this is actually what? Not 9 degrees, but what is it? 351 degrees. Okay? So, if I do 180 minus that, the equilibrium, it will be that value at that angle. So, 351 minus 180 is 171? No. Or yes, 171, right? So that's at 171 degrees. Does that make sense? Okay? That's the equilibrium. So we can see that we can add these vectors up like that. And they have components. If you go to the Schoology website, oh yeah, what the freak? Well, that's not working. Okay. You'll see under topic 1 that there's these packet corrections somewhere. There should be. Oops. Oops. I put them in the same place twice. All right, so on your packets, you see like we're going to do a problem off of there now on page 9 of 14. But when you look at that one, you would ask yourself, what does this mean? 1 centimeter key, AEE key. It's a little hard to understand. So something got messed up in it, right? So use a ruler and protractor for this. So, but we need the right scale. So if we look at the corrections, it says these are some of the 7 of 14. Some questions to the answers are wrong. Page 14 of 14. Some information was left off. 9 of 14, the key is screwy. Use 1 centimeter equals 1 centimeter and standard 360 degrees for the angle. So 1 centimeter equals 1 centimeter, and that's 0 degrees, and that's 180, and it go around to 360, okay? So use your ruler and your protractor to first tell me what the value of this vector is. I gave you an easy key, 1 centimeter equals 1 centimeter, so. Well, let's start with the length. Wait, too many people are talking to me. Caroline? 3.6. Do you agree? 3.5. Anyone else? 3.7. Oh, you do want to go all the way to the tip of the head. Okay? Let's try it again. All right. Well, we'll go with 3.6. Some people said 3.5. Some people said 3.7. So we'll go 3.6. Okay? Now, how about the angle? Marissa, you told me that. What was it? Well, no, it's not 40. Remember? Look at the key. 0, 180. So it's this angle right here. Oh, we don't know that angle simple yet. Well, you measure it and you tell me. What you get, Spencer? 140 degrees. Okay. Okay? Good. Now we're going to try one farther down a little bit. All right, well, what, 141? What did you get? All right, 142 maybe? Anybody got a stapler? Staple this to my ear? Not really. That wouldn't be just a bad joke. Now, we're going to try this one. I put one of those lines in it. It does that sometimes lately. It put this extra line in it. This means nothing, right? It's not on yours. And it says to draw this vector b such that a plus b equals c. Now, this is on the next page. So 10, right? 10 of 14. And it's 1.49. And now we want to draw b so that a plus b equals c. Now, whoops. So there's my a vector, right? If c is the what of a and b, the resultant, the sum of it. So we know resultants start where and end where. They start at the tail of the first one, and they end at the head of the last. So we know C here is going to have to start at the at the tail of A. See that? So I know to put C there, because C is the resultant of A plus B. Now, Spencer's going to come up and draw in B for us. If he can't do it, you'll help him. Good. So now we can see it, right? A plus B equals C. just to make it colorful. Okay. Okay, let's look at, talk a little bit about trig. Who got to the trig part on the video? Some of you? A good portion of you. So we just, who finished the video? A number of you, okay. If we have a triangle, a right triangle, right? We're not on anything right now, I'm just talking. We have a right triangle. We could have other angles other than the right angle, which is here. The right angle's value is what? 90 degrees, right? And we could have other angles, and when we have other angles, sometimes we call them theta. That's just a typical angle name. Greek symbol theta. So this thing here is theta. Okay? Now, we have the sides of the triangle, which we could just call well, what is this side called right here? The hypotenuse, right? Anyone know what we would call this side over here in relationship to theta? It's the opposite side related to theta. How about this side here that's next to theta, but it's not the hypotenuse? Not the hypotenuse, but it's still next to. We call that adjacent. Right? So there's some relationships that we can get from that. But first, let's step back a minute. Let's take our triangle and go back to when it was things like this. We all remember that, right? A, B, C. And what's the relationship that we can come up with that? Vera? Right. Pythag, right? Pythagorean theorem. Okay. So with the ratios of the sides of this, in this formula, we can do a lot with vectors. We can do components. We can sum them. We could take different vectors, find their components, add their components together, sum all the components in the x, sum all the components in the y, put them together and find the overall resultant. We can find the angle of that resultant using the trig ratios. Okay? So now, if we go to page 1 on here, the first problem, some of you have already done. Well, we could find out these lengths of these missing sides, right? Because this is the same, we could just use a squared plus b squared equals c squared, right? Where a is like 60 meters squared plus b, which is 10 meters squared, equals c squared. And 60 squared plus 10 squared is 3,700 meters squared equals c squared. Then we could take the square root to solve for c, and we would get c equals 60.83 meters. Right? Now, that's how we would find the hypotenuse in this. Say we had two vectors summed together. Say one vector is like this. One vector is like this. If you want to find the sum, like that, how would you go about finding this? It's 60.83 meters, right? So we could see if two vectors at 90 degrees sum together is the hypotenuse of the triangle. We would just use the Pythagorean theorem to get its magnitude. It doesn't give us its direction, but it gives us its magnitude. That equation, written out in long form, what's so funny? Did it? Did it fall? I don't know if that's funny. That's why one morning I came in last year and we found a little screech owl in the parking lot. Well, except it died. I mean, it was alive when we found it. And then we brought it in, and I brought it to the SPCA, and they euthanized it. I don't know. Maybe the screech owl. I'm not sure. No, it was broken before that. Yeah. Well, I don't know if you heard this, but they had a natural gas flame that burns off that they put in off the coast of Canada, and birds were migrating, and it was foggy, and they saw the flame, so they flew into it. It killed 7,000 birds in one shot, singed them all up. So it is a concern, actually, for wildlife of structures that humans put up in things. It's not just a joking matter, but actually something that they have to put in, there has to be impact statements before they design things like that so that they don't cause. If you stick a big giant flame, birds are drawn to lights in the middle of migratory paths of birds, then you can expect disasters like that. Well, yes, you could. If the flame was right and they were attracted to it. Yeah, well, it's natural selection unless there's tons of things that are put up where, yeah. Well, yeah, that would be, but there's not volcanoes erupt. There's not, 60,000 volcanoes going off at any one point, as there are probably some number of that of natural gas flames going off. So, and there's precautions that could be taken too. That's the thing in the building of those. Anyways, this formula on your reference packet that looks like I had it in my hand. What did I do with it? It's my old one. Okay, it looks like this. It's on the first page of your reference packet. Reference tables. Looks like this. Yeah. Now you look at that thing and you would say, "Oh my gosh, what is wrong? There's no way I could ever understand that, or whatever." Maybe you don't, but the initial math scare might be that. But what do we know by the structure relating this to this? What are we doing here? Right. So this squared and this is Pythagorean theorem, isn't it? Okay. So that's just all I want to point out at this point with it until I talk to you what the little sigma sign means. Crazy looking E. Okay, we'll talk about that tomorrow. But today I want to just point that out. Now, how would I go about to find this missing angle right here? Or missing side? Austin? So since this is like 50 meters squared, you should be thinking about going to that, oh my gosh. I gave you a test on Thursday, but we have that thing on Wednesday night. Forgot about that. I guess we'll have to have the test on Friday. Yeah. 62.45. That's that lecture I was talking about that I'd like you guys to go to if you can. And hopefully I'll have a bus. I should. I requested one. So we used the same formula as we did before, but how did I get 3,900 here? It's 80 squared minus 50 squared, right? When we bring that over to the other side, so we get that. Okay? And then the next one, you would solve the same way, right? Go through and do it. Okay? Now, if you have a triangle, we name some sides. Okay? We name that theta, and we call this the hypotenuse, H. This is the opposite, O, and this is the adjacent, A, right? Well, I don't know. I just drew it like that. Because that's what came in. It's not really that big of a deal. Usually I see them go back and forth with it. Okay? Now, you can have this triangle, see? Here. I could take this, if I could select it, and clone it. And I could make it bigger. Okay? Do I have the same O that I had from before? No, it's bigger, isn't it? Do I have the same A? No. Do I have the same H? No. However, there is something that relates to them. What is the same? The angle is the same. See? The angle is the same. The angle hasn't changed. The ratio of the sides are still the same because the angle is the same. So even though the sides got bigger, this side over that side is the same as this. This side over that side is the same as this side over that side. It hasn't changed for that angle. So the ratios stay the same. Now these ratios have specific names. The first one we're going to talk about is sine. And we say sine of an angle, and our angle here is theta. And sine is the ratio of what? Anybody know? Opposite over hypotenuse. Okay? Which is abbreviated sin, or S-I-N, not really sin. Sine theta, it's still read sine theta. Shouldn't, but without the E. O over H. Okay? What? Okay, no problem. Cosine is another ratio for an angle, in this case the angle theta, and that's the ratio of which sides? The adjacent to the hypotenuse. That's abbreviated COS theta equals A over H. Okay? So the ratio of A, the adjacent over the hypotenuse, is the cosine. This has the same cosine, this angle is the same as this cosine of this angle. Even though the sides are different lengths, the ratios are the same. Alrighty. What's our last one? Anyone know? Tangent. Opposite over adjacent. That's abbreviated TAN. Okay. Now there's a mnemonic that we put together to remember what these ratios are, which is just so ka toa. The sine of the angle is O over H, cosine is A over H, tangent is O over A. Okay. Marissa, do you play soccer? So Marissa hurts her toe in soccer, right? What does she do to it? Her sore toe. She soka her toa, right? Or you can remember Oscar had a heap of apples. That doesn't give you SCT though. Or the great Native American chief Sokotoa. When I was in geometry, my geometry teacher, who was like this woman about this tall in a skirt, and like old skirt, like, you know what I mean, like school marm, but good teacher. She made us follow her around chanting Sokotoa. So course, I did this in 5th grade, though. I didn't wait till I was in 9th grade like you guys. Actually, it was probably like 11th. I'm just kidding. It wasn't 5th grade. So, it probably wasn't 11th. It's probably about 9th. Yeah. But some of you are in UB math. They probably taught you this a long time back. Yeah, there's a UB math program. So, anyways, this gives you the ratio of sides in a triangle. So let's look. We can ask our calculator. They are all stored on here. Back when I did it, although we had calculators, they still showed us these things, which were books of all the ratios. Because now that's all stored in your calculator. So you could ask your calculator, if Carolyn wanted to, she could say, Celsius, what is the ratio of the opposite over the hypotenuse for a 30-degree angle in a 90-degree triangle? Or in other words, she would put sine 30, and it would tell her what that ratio is. So try it. Press sine 30. Everybody get your calculators. Tell me what you get. 0.5. So the ratio of the opposite to the hypotenuse is 1 to 2, or 0.5, or 2 to 4. If it's a bigger triangle, maybe it's 3 to 6. Maybe it's 3.2 to 6.4. If you didn't get that, there may be a reason. I could look at your calculator to try to help you. Did you put sine 30 and get 0.5? If not, raise your hand. It's coming some. It's probably mode. Can I see it? You got to change your mode. Try it. I don't know how to change it on yours. Anybody else? That? Okay. Yeah, stop complaining about it and get it done. Right? Every day. Didn't you say this like 3 weeks ago? All right. Yes. Inverse, right? So what is the sine of 0? Well, it's the opposite to hypotenuse. We're saying for a 0-degree angle, what is the opposite side? It's 0. So what would be the O over H then? It must be 0. How about sine of 30? Well, we found that one already. It was 0.5. How about the sine of 60? So we're asking the ratio of the opposite to the hypotenuse sides in a right triangle, right? For 60-degree angle, it's 0.87, right? Yes. Yeah, that's fine. Although it does say use your calculator, but that's fine. Whatever. Sine of 90. In this case, your opposite side is your hypotenuse, right? Well, if you did it differently, that's fine. That's okay. How about cosine of 0? 1, because now the adjacent is equal to the hypotenuse. 30? Okay. Or cosine 60? Cosine 90? Yeah, there is no adjacent. Tangent is 0? So tangent would be opposite over adjacent. If the opposite is 0, that makes that 0. Tangent of 30? Tangent of 60? Tangent of 90? Huh? Error. Well, because in that case, your opposite would be some number, and your adjacent would be 0. And if your adjacent is 0, can you divide by 0? No. So it says error or not defined. Okay. Good. So we could take a vector, okay, and we can do some things with it. So if we have just a regular old vector like this, it's at some angle theta to the x-axis, like that. So we'll just call this vector A. It can have to it these don't have to be dotted, I'm just doing it to show you so you see it. What's called the x component of it, AX, and what's called the y component. We've seen that, right? We did that with our vectors already graphically, right? X and y components, right? But now we have a way to find them. We can find them using these trig ratios. Start with the ratio for cosine. Cosine theta, what was our ratio for that? Anybody remember the mnemonic? A over H. SOHCAHTOA, ka. Adjacent over hypotenuse. Okay. Now, if we look here, cosine of theta, what is our adjacent for this problem? AY. No. AX, right? Because that is right here. That's the adjacent side. It's not the hypotenuse, but it's the other side that's adjacent to the angle. And then, what's our hypotenuse? A. Now, if I wanted to solve this for AX, what would I do? All? If I want to solve for AX, what would I do? Multiply by A. Good. Both sides, right? I should do that a different color. Just so I can see it. Multiply both sides by A. What happens here? So that's why we did it, right? So we get the formula AX equals A times cosine of theta. So if you want to mathematically find the x component, you just take the component's value and multiply it by the cosine of the angle. Okay? Now let's go to sine. Sine theta is equal to what? Opposite over hypotenuse. Sine theta, what's our opposite? AY. And what's our hypotenuse? A. So now, to solve for AY, I would multiply by A. And those would cancel. And now I get AY equals A sine theta. Okay? So these are two equations for the components. If you look at your reference packets, you're given a version of these in terms of R. It says Rx equals R cosine theta and Ry equals R sine theta. And that absolute value just means, it's not really absolute value, it just means in this case those two bars mean the magnitude of that vector, not its direction, times sine theta. Okay? So now we should have a clear understanding of three of those four equations and a partial understanding of one of them, if you have your reference packets out. So we know this, we know that, we know that, and we're getting to know that. You put your arrow over it. It's true. It is more correct with the arrow. Let's look at a problem. Where was that? Okay. On page 6 of 14, number 10. Okay, so it says A is 23 meters at 30 degrees. I'm just going to draw it in not with a scale, but just at 30 degrees approximately. So I'm going to do it mathematically, not graphically, okay? And the x component would look like this, AX. And you have to sneeze. You can use one of those. I ran out of both tissues yesterday. Yeah. And then AY is like that, okay? So those are vectors. So they have arrows on them. Well, sometimes they're left off, but it's all right. So what was my formula to find AX? It has a cosine in it. Okay? Now there's no cosine. Cosine always has to have an angle associated with it. You have a cosine of an angle. So in this case, our AX plugging in would be equal to A, which is 23 meters, the magnitude of A, times the cosine of 30 degrees. And then I would do it in my calculator. 23 times cosine parentheses 30 close parentheses. And I get out 19.9 meters. Okay? And then AY, what was my formula for AY? Sine theta, right? Now we know what the sine of 30 is already. What did we get when we did that? Remember? 0.5. So 0.5 would give us what, 11.5? I know, but I have to switch back and forth, you know? Like, so sometimes I'm here, but then I move over quickly. All right, so we have AX, 19.9, and AY, 11.5. All right? That's the component of A in the X direction is about 20 meters. And the component of A in the Y direction is about 11.5. And the Y would be positive, and the X would be positive as well. Now, find the components yourself of B. Draw it first so you can sort of see where it is. Find that, and when you get the answer, show me. And when you have the correct answer, you could go. I was hoping it was a little bit earlier so you could go a little early, but so much for that. Solve for B. Bx and by. If you're done, if you already did it earlier or something,